everyone. So yesterday, actually, Daniel was speaking about our pathway on modeling 2D materials, and this was his photo before. He has no idea about QMC stuff, and he has no white hairs at that moment. And then, I mean, he was very happy at that moment having some kind of a nice cluster. I mean, it's a decent size 1200 course. And then, but he managed to publish 4 or 5 QMC works from that cluster in 3 years. And so initially everybody was thinking that, hey, quantum Monte Carlo is, I mean, computationally expensive methodology. Yes, it is, but right now what we are facing is when we go to the large supercell sizes, DFT is actually the bottleneck for generating the wave function in our research. So yes, yesterday he was mentioning about what we have done. First of all, we have some kind of a study on 2D gallium selenide, how we managed to find the binding energies, optical, electrical gap properties, and lattice constants. And then we moved on to some kind of alloying stuff, and we propose a way of sharing gesture of parameters there in order to reduce the computational cost. And then we add a little bit more complexity. We started working on magnetic 2-dimensional materials, and first thing that caught our attention was manganese oxide, because we have an experimental data we can benchmark, and we come up in this work as well, where we have this U optimization, and then afterwards we get the Heisenberg exchange parameter from quantum Monte Carlo, and literally work on anisotropic parameters at the DFT level, and managed to come up with some kind of Curie temperature for this material. And it was literally, compared with the other DFT data, it wasn't matching, but we were matching the experimental data. That's a good sign. So afterwards, what we were thinking that how can we make our lives harder? So we were trying to find a material that that is harder than manganese oxide to work on. So we were looking at the literature, and we saw this material, vanadium diselenide. Why is it harder? So first of all, there are gazillion of papers published in fancy journals claiming literally different things. And the other complexity here is you have 2 competing phases of this material. So you have the magnetism involved, and you have the competing phases, and this is a correlated material. So this is what I can copy and paste from our paper. So everybody's some DFT work was claiming that, hey, the TC is at 290 Kelvin. Experiment was on the order of 455 Kelvins for the H phase of this material, and we have similarly T phase of this material, where experiments differ a lot in themselves as well, and it has fancy properties. So for the T phase, we have the charge density wave structure as well. So we said, hey, let's focus on this material. And recently there is a PRB paper about this. So they managed to find this weird looking cell. This is square root 3 times square root 7 supercell, where they observe some kind of charge density wave shift in this atomic shifts in the simulation cell. So we started looking at this. First of all, right now we have competing phases, right? So we have to know, and in the experiments, they put this material on different substrates. So we have to know the geometry of this material very well before we proceeding further. So beforehand, we were just doing some kind of lattice relaxations here, just increasing the lattice parameter a little bit. But what we have seen is that, okay, so this is the energy difference between T and H phases, and you have different functionals here. It's not only the lattice parameter affecting the energy difference, it's literally atomic positions are affecting our energy as well. And as we start applying strain to this material, and depending on the functional and the U parameter that you are applying, you are seeing different energy curves like this. So how can we solve this problem? So we literally knock Jason's door. Hey, can you help us with this? How? Generous. Sorry, how can we find the accurate geometry of this work? And then we conducted some geometry relaxations using surrogate Hessian approach here. And so this is our QMC data point here. And what we are seeing is that we have lots of different functionals here. And we are literally comparing the vanadium selenide bond length in the T phases here. So from what I see, just comparing this T and H phases, secant functional is getting relatively nice results for our position. And what we have found at the end after the geometry relaxation is the experimental measured value for the T phase is 3.4 angstrom. We are literally very close to it. We are 341. And for the H phase, it is experimental value. Again, these are all substrates by. And in France, freestanding wise, we are literally close to 335. And what we are seeing is that there is a phase transition as you start applying a strain to this material. So this might be a reason why experimentalists were reporting, hey, the ground state is H phase or T phase kind of stuff. So we have seen this here as well. So this is literally as you apply 5% strain to the H phase of the material, it prefers to switch to the T phase. And when you have the switch, you can observe this charge density wave structure as well. And there is a lot of thousands of data here if you are very interested in numbers, which literally are reported in figure in these plots. And then afterwards, we focus on the magnetic properties. So right now, for this geometry relaxation work, we only focus on the ferromagnetic case. And in the FT papers, we also saw that some people reported for formula unit 5 to 15 for magnetons here. So there is some kind of discrepancy here. So what we have done, we got a supercell consisting of 24 atoms here, and then we literally compare our spin densities here. What we are seeing is generally we have a minor negative spin direction in the chalcogenides here. It's literally minor value, so we can say, hey, it's close with the DFT functional, but for the DMC part and on the transition metal atom, we see huge differences here. So generally, this is PB plus U results. We are seeing that the magnetic moment is higher and it's literally closer to the core region, and it is similar for T and H phase here. So right now, what we can say for the ferromagnetic case, DMC literally finds lower magnetic moment on this structure. So afterwards, right now, we started focusing on different magnetic orderings of this material. So you have tons of different functionals and different U values here. So, and what we are seeing that it literally depends on your functional. And so we are also comparing the energy differences between the ferromagnetic and AFM cases here. And literally, we need something more robust. How can we do this? So literally, we managed to calculate the Heisenberg exchange parameter J with quantum Monte Carlo, and we figured that it is relatively large compared to manganese oxide that we previously find here. And when we benchmark our results with the other functionals as well, we find a nice trend here. Secant also gives relatively similar values for our Heisenberg exchange parameter for this one. Afterwards, what we have done, we have write our own developed code for magnetic Monte Carlo code here, and we try to estimate this Curie temperature in our Monte Carlo code. And what we have seen right now, it just only contains one parameter. We have the Heisenberg exchange. We are right now trying to improve it by DMI interactions and are including other anisotropic terms as well. But we see some kind of a nice shift from non-magnetic to magnetic case around 400 Kelvin. So this is also observed in the experiment. So this is a nice plus in our advantage as well. So this is literally random distribution of spin orderings at 400 Kelvin. But when we reduce it, you reduce it to 300 Kelvin, you start seeing islands of well-aligned spin directions in planar vanadium diselenide phase. And afterwards, we started looking at the charge density wave structure. So this is what we have found in the literature. This is a square root 3 by square root 7 structure, and you are seeing how transition metals atoms are shifted a little bit here. And in that work, they just focused on PBE functional and try to find if non-magnetic ordering is favorable, or it's the ferromagnetic case, or it is the Bayer T phase, or charge density wave perturbed T cases favorable. So we just run some different spin directions here as well, try to see what the minimum ground state is. So this is literally, we are benchmarking all these different functionals of charge density wave structures with respect to regular T phase of, regular non-magnetic T phase of vanadium diselenide here. What you are seeing, LDA literally consistently favors normal non-magnetic state over the charge density wave state. So this is not good, not aligned well with the experiments, because in this case they shouldn't, or we shouldn't observe this, and vice versa. PBE prefers the charge density wave geometry and literally favors the AFM state. But you have different magnetic ordering as well. So is it literally ferromagnetic case or the AFM state? So what we have done right now, we literally change our reference point. We literally change it to non-magnetic charge density wave structure. And from these energy differences with the different functionals, right now what we have seen is that non-magnetic cases least favorable except the LDA functional here. So LDA prefers to be in the non-magnetic state in U equals to 0. And afterwards, we have the FM structure, but we have competing non-magnetic ordering here. So next step, so this is on the DFT level, but next step, what we are aiming to do is literally calculate these exchange parameters with quantum Monte Carlo for the charge density wave structures as well. So what I have shown here, so here is the R group's trajectory on modeling these 2D structures, starting from simple cases to increasing complexity here. And in the future, what we want to include is some kind of spin-dependent alloying that we have experienced before as well. So we want to add a spin-dependent dimensionality in those directions as well. And this is Michael. And yesterday, I was also talking with Daniel about it. So he literally carried most of the work for this work. And he said that all of these people in this screen literally changed positions during start to the end of this project. So he graduated, became a postdoc at NIST. Kayan joined Oak Ridge Nation Lab. Jeremy's stable. And I mean, I got a promotion and you have changed a position. And the undergrad working in this work wasn't born at that moment when we started this project. Okay, guys. And if you are interested in joining my group at any career stage, please let me know.
Thank you very much. Open for questions. Oh, that's some questions.
I get a question.
But go ahead, Mika.
So is it true that PPE plus you always prefers antiferromantic state?
FM state, not AFM state. For the charge density waves.
Okay, so actually even but then when you had the difference between the two structures, then it was antiferromantic or ferromagnetic.
So there is an energy difference between ferromagnetic and AFM state, but in most of the cases, PB prefers FM state.
And the big question, when you had a crossover with the strain, how did it look like in the different DFTs that crossover? Especially if you would like enforce the right magnetic ordering, but you would just do the crossover.
So in this case, these calculations are only on FM.
Only on
So it's not AFM. So we have to check
okay.
how the magnetic order changes with the strain.
But the crossover was incorrect in all the cases.
Yeah.
Except the scan seems to be very good.
Yeah, we are observing similar stuff here.
So the scan was like the best one.
Yeah, where was the one? Yeah, this thing.
Yeah, that's close.
I'll open for other questions, also online. And I certainly have some questions. All right, so this may be tricky to answer because it's on the DFT side, but I'm wondering if you have some reasoning on this. So, we know that scan fails for magnetic metals, right? Unfortunately, this was pointed out by David Singh, and people have seen similar things in other magnetic systems, right? But there are some magnetic systems where it seems to do, quite well for exchange constants and moments. So, do you have, any sense based on the wider knowledge of the literature, in addition to the calculations, as to when it might be reliable and when it might not be reliable, or is this just more argument for quantum Monte Carlo calculations at this point?
So actually, last week we were discussing about this, and I was asking Daniel and my student about, hey, can we look at the density of states active around Fermi levels? So is there some kind of predominating effects of these states around the Fermi levels? So maybe that might be a start point for an analysis, but right now I don't have a definite answer.
Thank you. Time for a quick additional question. Go ahead.
Thank you, and very nice talk. My question is more technical. You using DMC scan function, wave function, or
PB plus U.
PB plus U?
Plus
Would there difference if you use scan? Or...
the main reason that we didn't use scan is it was problematic with the convergence. So we said, hey, let's go with PB plus U.
I've done a bunch of work with R2 scan recently, and that certainly has better convergence. But if you have a very large plane wave basis, of course, that's still expensive. So.